It's tempting to think that most AI failures in production come from bad models, but usually something else breaks first. The model could give a perfect answer to the wrong question if it looks in the wrong place for context. Imagine you're running an online clothing brand, and every single day your support inbox fills with the same types of questions. Will this fit me? Is it true to size? Can I return it if it's not? The answers exist. They're just scattered everywhere across reviews, FAQs, internal knowledge base articles, and finding them fast and at scale is the real challenge. Many teams turn to large language models, but in practice, their answers are only as good as the context that you give them. And that raises a really interesting question. If you have hundreds or thousands or even tens of thousands of documents, reviews, or FAQs, how does the model know which ones actually matter for the given question? Now, humans resolve this ambiguity almost instantly. But how does a model do it? And how does it do it at scale? That's what this video is about. Retrieval-augmented generation, or RAG. When it works, it can feel almost uncanny. But under the hood, it's just simple geometry, points, arrows, and distances. In modern language models, every single word, sentence, or document becomes a single point, not on a page, but in a space with hundreds or even thousands of dimensions. Each dimension represents a small aspect of meaning, like tone, or topic, or intent, or formality, kind of like axes in a 3D space, just many, many, many more of them. Now, we can't picture hundreds of dimensions all at once, but we don't need to. If you understand 3D, then you already understand this higher dimensional space. Imagine a piece of text is represented by a point, and similarity is just how close are these points to one another. And for intuition, let's start small. Not with hundreds of axes, just two, the XY plane, and let's imagine points on a unit circle. With the unit circle, every point is exactly 1 unit away from the center. Now take these two arrows. One points right to the coordinate 1, 0. The other points in some other direction. Are these directions that they're pointing in close? Are they completely different? How do we tell how similar these directions are? Well, imagine there's a flashlight shining downward onto the x-axis. The light will hit the top arrow first, and then cast a shadow down onto the horizontal arrow. The length of this shadow is directly related to how much these arrows actually point in the same direction. That shadow's length is exactly the cosine of the angle between the arrows. It's also called cosine similarity. When the arrows completely overlap, cosine's 1, and the shadow covers the horizontal arrow entirely. At a right angle, cosine's 0, and given the orientation of the vertical arrow, the shadow length is 0. When they point in opposite directions, cosine's -1, which means that these arrows are kind of maximally opposed. As this moving arrow rotates, you'll notice that the shadow is growing and shrinking, and kind of get the sense that it's measuring a sort of similarity. Small angles correspond to greater similarity, large angles correspond to greater dissimilarity. Now, cosine distance is actually a very related concept to cosine similarity. It's actually defined as 1 minus cosine similarity. You can kind of think of it like a distance metric rather than a similarity metric. It's 0 when the arrows are perfectly aligned, 2 when they're maximally opposed, and then it smoothly varies in between. Now, if we imagine these points on the unit circle actually represent pieces of text, then cosine similarity and distance should intuitively tell us how aligned their meanings are. For example, cat and dog are very related concepts, and if they were both individually represented by arrows within our unit circle, they should have a pretty small angle between them. But cat and car, those are very unrelated concepts, and you might imagine that their arrows would be roughly perpendicular. For opposite concepts like hot and cold, the arrows might also point in opposite directions. Now, the unit circle only gives us 2 dimensions to work with, and intuitively real language doesn't live in just 2 dimensions, meaning could span many dimensions all at once. So let's add a dimension. Instead of a flat circle, imagine everything living on a 3D sphere. Each small patch on this sphere represents an individual piece of information, like a conversation, a document, an FAQ, or a review. Some patches naturally cluster together, while others drift further apart. Patches that sit near each other should represent similar things, and the arrows that point at these patches should have a small angle between them. Now pick any points on the sphere. There's a shortest path that you can trace on the surface between the 2 points. The shorter the path, the more closely related those 2 pieces of information are. Now say a new question arrives from a customer, who may or may not be me, and the question states, what tuxedo should I wear to this wedding? I'm 6'2", but I have really large legs. Since the question is only text, it has a natural location on this sphere. Now say that location is represented by this yellow patch. When our system is trying to find the right context to pair with our question, it's not using keywords or explicitly hard-coded rules. It asks a simpler question. Which existing points lie closest to my question? The light blue patches are reviews and documents and other pieces of information. Some are really close to the question, and then some are really far away. The nearby ones, or the nearest neighbors, are the ones that really matter here. They could represent reviews of similar folks who may be tall with big legs, or FAQs about tailoring, or knowledge-based articles that may be relevant. And the large language model can inject those matches into the prompt to inform its answer to your question. Now, cosine similarity, which is related to angles, and these spherical distances are very related concepts. Smaller angles yield shorter paths, and larger angles yield longer paths. Now, how do words actually become points in the first place? Now imagine that the lowest level pieces of text, like words or subwords that the model works with, are each assigned a really long list of numbers. And you can think of it like some coordinate in a really high dimensional space that this arrow is pointing to. Now we'll call these token embeddings, or the vector representations of the text units that the model works with. These vector spaces are really huge. They can be hundreds, sometimes thousands of dimensions, and we can't really visualize them like we do 2D or 3D. But they're governed by the same geometry that we went over with the 2D circle and the 3D sphere. At the very beginning of training, these embeddings don't mean anything yet, and these arrows are pointing almost in random directions. Words like cat, dog, and car are scattered about this space, and there's no inherent structure yet. And the arrows that point to them are pointing in random directions. To us, these words are loaded with meaning. But to an untrained model, they might as well be gibberish. Then training begins. The model is going to read a block of text and then try to predict the next word. Every time it's wrong, something subtle happens. The model will adjust its internal representations and rotate these arrows gradually to reduce future mistakes. Now, one way this happens is when 2 words show up in similar situations, the model will actually nudge their arrows in similar directions because treating them similarly helps reduce future mistakes. For example, if the model repeatedly sees sentences like, the cat chased the ball, and the dog chased the ball, learning what tends to follow cat should intuitively help with dog. And even though cat and dog were randomly situated in this space when training began, as training progresses, they get pulled to a shared region of this space. And across billions of examples, words that are semantically similar naturally cluster together. Now the funny thing is, nothing in the code ever defines what a cat is. The meaning isn't written down anywhere. It emerges from these geometric transformations. Now that words are arrows in a really high dimensional space, how do we know that 2 words mean similar things? Well, we already have that intuition from 2D circles and 3D spheres. Similarity is just the angle between them. And in hundreds of dimensions, the idea is the same. Cosine similarity measures that angle, telling us how aligned our vectors are. Let's pause for a moment. A single word could have multiple meanings depending on the context. Take the word bank in the sentences, John deposited money at the bank, and John fished by the river bank. It's the same word, but clearly 2 different ideas. Now imagine that we force bank to live in a fixed point in space, that no matter what sentence it appears in, the arrow that represents bank points in the same direction. If we did that, both of these sentences would collapse onto the same meaning, and the river and finance concepts would blur together. But that's not how language works. But lucky for us, that's also not how language models work either. So let's see what happens. With transformer-based models, specifically through the self-attention mechanism, a word doesn't come with a stagnant arrow attached to it. Instead, its arrow is rebuilt every single time it appears, and it's influenced and shaped by the words around it. Watch what happens to our word bank. In the first sentence, words like deposited and money start to tug on bank, and the arrow shifts, not to some random region, but to a region associated with finance. In the second sentence, the words river and fish pull on it, and the arrow bends in a completely different direction. It's the same word, bank, same spelling, but we have two different arrows pointing in two different directions representing completely different concepts. That's the core idea behind contextual embeddings. Semantic meaning isn't just stored in a word itself. It emerges from a word interacting with its surrounding context. And this geometry doesn't just stop at individual words. Once every single word has shifted into its context-shaped direction, the model takes a step back. It looks at all those word arrows together, represented by their coordinates. You can think of them kind of like many small forces pulling in slightly different directions, and the model has to learn a way to combine all these small forces into a dominant direction, kind of like a fused concept. That final arrow, that final dominant direction, represents the meaning of the entire sentence. So the sentence "John deposited money at the bank" isn't just a collection of word embeddings. It collapses into a single embedding that represents the entire idea. We didn't design a super complicated search system. It emerged pretty naturally from geometry. All your long product reviews, FAQs, internal documents are each individually mapped to this same vector space, just in different locations. At this point, finding the relevant document pertaining to my question is not about using keywords anymore. It's the same question that we asked with the unit circle and with the sphere. Which arrow points most closely in the question's direction? When your customer asks a question, the question's embedded, or it's turned into an arrow pointing in some direction in the same space as your documents. At this point, the system does one thing. It compares your question arrow to all the document arrows. Using cosine similarity, it determines which document arrows are pointing in the most similar directions to that of the question arrow. Those nearest neighbors, the reviews, the FAQs, the internal documents, they're pulled out and handed to the language model as additional context. Only then does the model generate an answer. That loop of embed, compare, retrieve, and generate is what we call retrieval-augmented generation, or RAG. The model does not need to memorize everything. It just needs to know where to look. I really hope you found this helpful. Let me know what you think, and I'll see you in the next one. Peace.